This is the part 3 of pre-calculus review. In this review, we're going to talk about two major topics, the polynomials and rational functions. Um, so we're going to spend the first few minutes for the polynomials, and then we're going to go for the rational functions. And then after that, we're going to talk about inequalities. And under inequalities, we're going to talk about how to solve polynomial inequalities and the rational inequalities. So the topics include, so let's look at the first problem. So it says that the graph the following polynomial using the n behavior, the number of turning points, and the nature of the graph near zeros. So those are the three facts we can use. So let's talk about the theory a little bit. So let's talk about major theories of a graph of a polynomial function. So so we have a polynomial, I'm going to call it fx, so which you can write as an xn plus some terms and then the constant term a naught. Because you can see that a naught is the y-intercept, because if you plug in x equals 0, all the previous terms get cancelled and you get a naught, so which is the y-intercept. And then you know that we learn about this idea. For example, for large n, this polynomial gonna behave like a n x n. So for large n, both positive and negative, that's why it's absolutely. So what it says that the for large x, you can see the function behaves almost like the leading term. This sometimes we also call the end behavior. So that's the name we use for that, the end behavior. End behavior. So when you talk about end behavior, we can talk about n even and then n odd. So those are the two cases. So if n is even, we also need to consider another two cases. What happen if a n is positive, and what happen if a n is negative? And the same thing happens here. And then we also need to know what happens when a n positive and a n negative. So we know that when n is even, the graph gonna go to one direction, either gonna go to positive or negative. So if n even and also a n positive, the graph gonna looks like gonna go to infinity and then some behavior depending on the rest of the terms and gonna go like that. So that means both for negative infinity and positive infinity graph gonna go to the large x to the positive side. And then for a negative, what's going to happen? It's going to flip over. So that means the graph going to go to negative infinity and then some behavior and then go like that. So that is the shape of the graph for n even and n positive and n negative. And if n odd, so this is for n even. So if n is odd, what happen? So we normally call the odd dance. So it's going to go like uh, that's for negative and then some behavior and positive. So it's going to go like that. And then for n odd and a negative, the graph going to go like this way and then going to go like that. So, because this side we don't know, it's depend on the rest of the terms, and then going to go like that and then go to in infinity. So like this. So this is what we call the end behavior. So you can see this is for the large x. So it can be x can be going to a positive infinity, or x can go to negative infinity. So either positive infinity or negative infinity. So this is the behavior. This is what we normally call the end behavior. So next, let's talk about what will happen near zeros. So So there are two cases to consider. So one is a 0 with an even multiplicity, 0 with an even multiplicity. So if the 0 with an even multiplicity, what will happen? So the graph can be in two ways. So either the what will happen in this case, the graph gonna touch the x-axis at the 0. So if you call the 0 is a, so it can be like this or it can be like that. So it can be one of those cases depending on the rest of the function. So it's going to touch the graph. And then if the 0 has an odd multiplicity, so 0 with an odd multiplicity, so what will happen in this case, the graph gonna cut the x-axis. So it can be either this way, so it's going to cut at a, or it can go like that, depending on again the rest of the function. So in this case, the graph gonna cuts the x-axis. So if there's an even multiplicity, the graph gonna touch the x-axis. If there's an odd multiplicity, the graph gonna cut the x-axis. So that's what we call the behavior near 0. And then the third one, what we're gonna do, we're gonna talk about number of turning points. So what it says that the graph of a polynomial of degree n can have at most n minus 1 turning points. The turning points sometimes we also call local maximum or local minimum. So what the theory says, the graph of polynomial of degree n can have at most n minus 1 turning points. This idea will be clear when you try to take calculus. In Calc 1, the turning points we normally find by taking the derivative. Once you take the derivative, degrees decrease by 1. And that is the reason why we have n minus 1 turning points. So let's write it. So what it says, the graph of a polynomial of degree n can have at most n minus 1 turning points. Those turning points are what sometimes we call the local maximum or local minimum, or sometimes called local extreme. Those are the terms we use for that. So for example, for example, so let's say you have a polynomial fx, which is ax cube plus some terms. So this is degree 3. So that means if you look at the graph of this function, it should be like this. It can have at only two turning points. So there's a one turning point and another turning point. So it should be like that. So there can be only two turning points. There's a one here and there's another one here. Because it's degree 3, can be one less means 2. So and then so that means if you have a graph like this, let's say you have 1, 2, 3, 4, 5. That means this can never be a graph of a cubic function. The reason is you can see there are a lot of turning points. There's a 1, and then 2, and then 3, and 4. That means this has to be at least degree 5. It should be at least degree 5. So at least degree 5. Good. And then if you look at another type of problem, let's say you have a graph like this. So this is the graph. Say this one, go down, go up, go down, like that. Now the question is, what is the least degree this can have? So since there are 3 turning points, so this should be and also it should be even degree polynomial because it's a graph going into the same direction, even degree with at least degree of at least 4. Okay, so we can see it should be a polynomial should be a polynomial of even degree, because it's going to the same direction, even degree, with a negative leading term, with a negative leading term, with a negative leading term, and of at least you can say degree 4. Degree 4. The reason is there are 3 turning points. So that's how you use this idea. So now let's try to look at the problem one by one and see how we can solve them. So we can look at the first problem, which is the graph the following polynomials using the end behavior and the nature of the graph near the zeros, and also we can use the turning points here. So the first problem is quadratic, and we can use the technique that we learn in this uh, chapter. So what we normally do is we try to find the complete factorization and then use the factorization to graph the function. So what we normally do, if we get like a constant like that, we can pull the negative sign out. So you're going to get 2x squared minus 3x plus 1, and then we try to factor this. And then what are the factors? So this is not that difficult to factor. So you can see that so you have the number 2 because it's 2 times 1, which is 2, and then so you're going to find two numbers. When you multiply, you get 2, and when you add, you get negative 3. So the two numbers are negative 2 and negative 1, and then that's directly going to give you the factors. So that means you can say negative. And how to write the factors? So what we normally do, we can look at the leading term. So leading term is 2. So because of leading term 2, we can write this one as 2x and x. So the goal is to find the constant term. So what we're gonna do, we're gonna divide the appropriate number by the leading term. So that means you can see that you can divide negative 2 by 2. So therefore, if you divide negative 2 by 2, you get negative 1 if you write on the other side. And then the leading term of the other one is 1. So if you divide 1, so negative 1 by 1, you can see you get again negative 1. So those are the two factors. So that's the easiest way to find factors. After you find these two numbers, simply divide by the leading term. That's going to give the constant on the other side. So for example, question is how you get this one. So to get that one, what you're going to do, you're going to divide negative 2 by 2. That's how you get the one. And you can see that you cannot directly divide a negative 1 by 2. So we don't do that. We pick the one that you can divide. So because after you find the two terms, we can write it the factorization 2x minus 1 and then x minus 1. And then we also try to have in each factor 1 as the coefficient. To do that, we're gonna divide the first factor by 2, or we're gonna take 2 as a factor out. So if you do that, you can see this one negative 2. I pull the 2 out. That means you divide everything inside by 2, only the first factor. That means it's gonna be x minus, if you divide 1 by 2, then 1/2. So that is the easy way to do that. The reason is this is gonna give you the two zeros directly. So that is 1 0 is 1/2. That means we know that at the zeros the graph gonna cut the x-axis, so we can use that idea here. So that means so it's 1/2 and 1. So those are the two numbers this graph gonna cut the x-axis, so we can use that fact to graph. So that means so we have those the axis, and then we have those two numbers. So what are the two numbers? 1/2 and 1. So we're gonna put those two numbers here, 1/2 and 1, and then now we can graph the function, because the function has to pass through these two numbers. So that means and it's a parabola, so it's gonna go like that. It's gonna pass through and go down. So that is the shape of the parabola, and this is 1/2 and this is 1. And also you can find the y-intercept always just plug in x equals 0. So in this case it is negative 1. So that is the graph of the function using the zeros method. You just use the zeros, and you can see that they have multiplicity 1. So multiplicity 1 means they have to cut the x-axis, and that's exactly what happened at the two. So you can see it's going to cut the x-axis at those 2 points because they are odd multiplicity. That means you have to cut the graph. So and then you can see that polynomial, if it's a quadratic, they always have two factors. That means they are all odd multiplicity, uh, like that. And also it can repeat. If it's a repeated one, and you know that it's going to touch the x-axis if it's repeated, because even multiplicity. But in this case, the odd multiplicity, they're going to cut the graph at that point. So that's how we use the zeros to graph a quadratic function. So let's look at the second problem. So we have gx equal 3, x minus 1, x plus 2 to the fourth power. And you can exaggerate a little bit, and you can write this one as x, uh, 3 times x minus 1. You can write this one as x minus 2 to the 4 to exaggerate the 0. So the one 0 is 1, the other 0 is negative 2. You don't know how to do that, but you can do it. Okay, and then also we need to know what is the degree of the corresponding polynomial, and you can see that this can behave like so the leading term is 3, and then what x terms you get, and you can see from the first factor you get x term. From the second factor you get x to the fourth power. So that means if you multiply, this equals 3x to the fifth power. So that means this polynomial gonna behave like 3x to the fifth power for large x. For large x. Good. So we can see that a equal 3, which is positive, and degree, you can see it's a degree of 5 polynomial. So that means the graph gonna look like this, and then some behavior, and gonna go like that. So that is the end behavior for this function. And also let's look at the nature of the zeros, and you can see the zeros and the multiplicities. So we have so the zeros. So we have x equal 1 with an odd multiplicity because the number is 1. So uh, with an odd multiplicity, and then where x equal negative 2 with an even multiplicity. So we know those two facts. So that means at x equal 1, cut the graph, and then at x equal negative 2, it's gonna touch the graph. Okay, so that means at 1, so it's gonna cut the graph, and at negative 2 is gonna touch the graph. So now we can use those four information, actually those two information, the shape of the end behavior and the nature of the graph near the 0 to graph the function. So so again, so what happened at x equal 1, you can see that the graph gonna cut, so it can be either this way or that way depending on the rest of the function. And again at x equal negative 2, it's gonna be either going like that if the graph is coming from the top. If the graph is coming from the bottom, it's gonna go like that. So it depends on the rest of the graph. So let's try to use these facts to graph the function. So these are the axes, and then we have zeros. So we're gonna so what are the zeros? We have 1 as 1 0, and then negative 2. So negative 1, negative 2 as the other 0. And then what else we know? So we know that the graph gonna go like that and like this. That's also gonna help you to figure out what is the shape of the graph. and then that means it has to be um, over here, it has to be like that, and then at 1 it has to go like that. So once you know those information, now we can graph the rest of the function. So after we connect it, so we're gonna get a graph like this. So we're gonna connect them, go like that. Actually, yeah, I'm gonna draw like this. So it'd be better to extend the graph like that, and so it's gonna go down and then take a turn and then go up and go like that. So there's one difficulty when we use this idea to graph, and we exactly don't know where this turning point happen. Because there's a turning point, we know that there's a turning point, but we don't know where this happened. For that, we need calculus to figure out what is the exact point. But for pre-calculus, we cannot exactly find that point. But we know that there can be only two turning points, because actually this one has 5, so degree 5, so that means it can have 4 turning points in theory. Um, so that's also we can exactly say until we take calc 1, then we can say what is the exact number. Okay, so this is how we use the idea, and you can see that there's a at -2 the graph touched the x-axis, at 1 graph cross the x-axis. The reason is at 2 the multiplicity is even, at 1 the multiplicity is odd, and then we also use the end behavior here. So that's how you graph a polynomial using those ideas. Good. So let's go to the next problem. So at part C, we have hx equal -2 x plus 1 squared x minus 3 to the 5th power. So that means in the long run, this is going to be -2. You get x to the squared from the first one, and then you get x to the 5th from the second one. So that means if you multiply through, you get -2 x to the 7th. So that is the long-term behavior. So you can see, so in this one we have a equal -2, so which is negative, that is the leading term, and then n has degree, so you can see it's a degree 5, degree 7, so degree 7, so which is an odd number, it's an odd number. So that means the graph is a negative leading coefficient with a odd degree. That means the graph should look like this. It's gonna be like that, and then some behavior, and then go like that. That has to be the shape of the graph. And then we also need to look at the zeros, and then you can see so there are 2 zeros. So we have x equal -1 with even multiplicity. So even multiplicity, because we have 2, and then we have x equal 3 with odd multiplicity. So and then so because of that we know at the even multiplicity, so graph gonna look like either this way or that way, depending on the other terms. And then at the odd multiplicity, so it's going to cut the graph, so it can be either going like that or going like this, again depending on the rest of the function. So we can use this information to graph the function now. So we have so these are the axes, so we can mark the 2 zeros. We have one at -1, the other one at -3. So -1 and -1 and 3, and then also we know the end behavior is gonna go like this and gonna go like that, and because of that because at -1, which is an even multiplicity, so the graph should go like this. And then at so it's gonna go like that, and gonna come back at some point, and then this should be going like this. So we know those two information. Now we can use those idea to finally graph the function. So we can see that the final graph gonna look like this. So this is -1 and 3. So it's gonna go like this, and it's gonna touch the graph, and it's gonna go there and go pass through that point. So only thing, again, we don't know where this local maximum is. For that we need calculus, but otherwise we have a pretty neat graph. So this is -1 and 3. So at -1 it's going to touch the graph, at 3 it's going to cross the graph, and also we can find the y-intercept here. To find the y-intercept, just plug in x equals 0, and you can see if you plug in x equals 0, what you're going to get is -2 times -3 to the 5th power. That's a large number, and we can calculate this number and write it here, so you can see it is positive. So this is 2 times 3 to the 5th power. Good. So that is the graph using the end behavior and the nature of the zeros. And also we can make one more argument here. So this is not exactly accurate here at 3. So because the reason is, you can see there x minus 3 to the 5th power. So when you have a larger power, even though it's gonna cross the graph, it gonna more look like this. It will more look like, so at 3 the graph gonna look like, when they have larger powers, it's gonna go like this. It's gonna go and then go like that. So even though it's cross, it's gonna cross like that. So it's like it's not like you draw a line through it. So that's what happened at 3, but we are not going to exaggerate that much. But that's the shape of the graph. It's gonna go like a tangent to the graph, to the x-axis. Okay, so that's about that. So let's do the next one. So as the next problem, we have kx equal -2/3 x squared x minus 1 x plus 3. So we can exaggerate, this is x minus 1 to the first power. So we have for this problem we have a equal -2/3, which is a negative number, and the degree, so you can see if you count the x terms, we have x squared and x to the 1 and x to the 4th power. So if you add all the powers, you're going to get 2 plus 1 plus 4. So we have 2 plus 1 plus 4, which is 7. So it is a degree 7. So because of that, it's a negative a and a degree 7. That means the graph should more or less look like this. So the graph can look like this. So we have going like that, and then some terms, some behavior depending on the rest of the function. So going like that. So that's the shape of the graph for odd degree and negative leading term. So let's look at the zeros now. So we have 3 zeros in this case. So we have x equals 0. Because x squared means x equals 0 is a 0. So with even multiplicity, that means at x equals 0, they're gonna graph gonna go either this way or that way. And then we have x equal and then 2. with uh, say x minus 2 to the 1, so that means odd multiplicity. So odd multiplicity, that means at 2 gonna graph gonna go like either this way or that way. So again, depending on the rest of the function. And then we have x equal negative 3 with even multiplicity. Even multiplicity. So that means at negative 3, again gonna graph gonna go like this or like that. Good. Uh, so using all those information, now we can have a first we have a rough idea, so we can see we're gonna mark the zeros and we're gonna figure out what is the shape of the graph. One thing is let's put the zeros in the order. So we have negative 3, and then we have 0, and then we have 2. So those are the 3 zeros. And then the end behavior says that the graph gonna go like this and like that. And then at negative 3 is an even multiplicity. That means the graph gonna, because it's going like that, so graph gonna go like this here. And at 0, which is also even multiplicity, so that means graph has to go like that. And then at 2, the graph gonna is a odd multiplicity at 2, so it's gonna go like that. So this kind of tell you what is the shape of the graph, and then we don't know where those peaks or the turning points happen. So we only know 2 turning points, but we don't know what happened at this turning point and that turning point. Thus we need calculus for that. So using this information, now we can finally graph it. So we can get a much accurate graph now. So we have negative 3 and then 0 and 2. So let's use all this information to get a graph like this. So it's gonna go to infinity. It's gonna touch at negative 2, and then gonna go up and touch at 0, and then go up and pass through. Actually, we need a little bit accuracy here. So yeah, it's gonna go up, and it's gonna go there and go and pass through 2. Again, we don't know anything about these two peak, whether it's at the same level or any other. With that, we don't know. We cannot do that using pre-calculus ideas. That need more advanced ideas for that. So only thing we know is it's a touch at negative 3 and touch at 0 and cross at 2. Okay, so that is the graph of kx function. And let's go to the next one. And the next one, what it says, it's not in factored form. So let's look at that. So as the next one, we have px equal negative 6x cubed plus 30x squared minus 18x minus 54. So the difference between this problem and the previous problem is, in the previous ones it was already given in factored form, but right now it is not in factored form. So what we can do, we can find the end behavior, because this gonna behaves like negative 6x cubed for a large x, that we know, but we don't know where those zeros are. So that means what we can do, we're gonna factor. So to factor, what we're gonna do, we're gonna use the guessing method. So we're gonna plug in a few values to the function and see whether it's gonna get 0. So for example, we can plug in 1. So if you plug in 1, what do you get? You're gonna get negative 6 plus 30 minus 18 minus 54, and you can clearly see that this is not actually this is negative 48, which is not equal to 0. That means 1 cannot be a factor, and then p, we're going to plug in -1. So those are the first two values we normally plug in to a function. So which is -6, -1 cube plus 30, -1 squared, -18, -1, and then -54. If you simplify, we know that if there's an odd power to the -1, it can switch the sign. It's the even power, it does not change the sign. So we can use that idea. That means this is going to be 6, and then plus 30, and then we have plus 18, and then minus 54, and you can see this is 0. So what does that mean? Since this is 0, this should be a 0. -1 should be a 0. So that means x plus 1 is a factor. So this is what we normally call the factor theorem, and we're going to talk about that later in another problem. So since we know one factor, what we can do, we can divide by this factor to find the quotient, and that quotient, then we can factor the quotient. So that's what we're trying to do. So you can either use a log division or synthetic division. So we can use the synthetic division because that's much quicker. For the synthetic division, we only need the coefficients. So we can write the coefficients of the px polynomial, which is -6, 30, -18, and 54, and then we divide this one by x plus 1. When you do that, we write the 0 here. So what's the 0? It's -1. And then we're gonna copy the number, the first number down, and then multiply the two numbers and add. So we're gonna multiply these two and add over there. So that's what's gonna happen. So in this case, when you multiply, you get 6, so you add, and then when you add, you get 36, and again when you multiply, you get -36. When you add, you get -54, and again we multiply by -1 and add, you get 54, which is 0, and it should be, because since x plus 1 is a factor, it should divide completely, so you should get a 0 there. That confirm that this is right. Okay, so this means that this is the quotient. So we have the quotient right here. Now we can write the polynomial in this form. So we have first factor, which is x plus 1. The second factor is -6x squared plus 36x minus 54. Since this is quadratic, we know how to factor this. So the best thing would be we can pull this -6 out, because you can see it is common. So we can pull this as a factor. So that means you can take -6 out, and we rewrite x plus 1. Pull -6 out means you divide everything by -6. You get x squared -6x plus 9. And you can see this one you can factor completely. That's a complete square. Also, it's very easy to find the two numbers, because what we have is you have 9. You should find two numbers. When you multiply, you get 9. When you add, you get -6. The two numbers are -3 and -3, and those are the factors. That means you can write this one as -6, x plus 1, x minus 3, x minus 3. That's what coming from the last factor. So I'm going to write the rest of the work here. So actually, yeah, so now what we can do, since we have the complete factorization, we can write it like this now. So we have px, which is equals to -6, and then x plus 1, and then x minus 3 whole thing squared. That's what we have. You can see the leading term is -6. So this problem a equal -6, which is negative. And also what's the degree? And you can see that this is x to the 1 and x to the squared. So the degree is 3. So degree 3. And now we look at the zeros. So we have x equal -1 with multiplicity 1, so it's an odd multiplicity. So that means the shape has to be should pass through the graph like that at -1, and then we have x equal 3 with even multiplicity. Since the even multiplicity is going to touch the graph, so it's going to go either like this or like that, depending on the rest of the graph. So we use this information to finalize the graph now. Um, so we have two zeros, uh, one at -1, the other one at 3. And also we know the end behavior, it should be like this and like that. And also, so because of that, and also the even multiplicity at a -1 is an odd multiplicity, they're going to cross the graph like that. And then at 3, which is an even multiplicity, uh, so we have uh, a graph going like this. Okay, now we can use this information to finalize the graph. So if you connect them, it's gonna go like this, gonna go like that, and it's gonna cross at some point that we don't know, and then gonna go like that, and gonna go. Okay, so that's the shape of the graph. And again, we don't know where is the turning point. So that's the shape of the graph. So it's a touch at 3 and cross at -1. And also we can find the y-intercept if you plug in the value 0. So you can see if you plug in the value 0, you get -54 as the y-intercept. So that is the shape of the graph. Okay, so let's go to the next problem. So the question says, find the real zeros of a polynomial. Find the real zeros of a polynomial. So if you want to find the real zeros, there are several major tools that we use. The most common one is the factor theorem. And then when you want to use a factor theorem, we also use the rational roots theorem along with that. And then also we need to know how many roots are possible. For that, we're going to use what we call the Descartes sign rule. And then also we use the synthetic division or the long division along the process. So let's discuss them one by one. Find real zeros of a polynomial. So let's say we have polynomial fx, which is we write that as a in xn, and we have some intermediate terms and a constant term a0. So let's start with one by one. So the first one is the factor theorem. The factor theorem says that if c equals 0, that means when you plug in a value c, if it is 0, then it says that x minus c should be a factor of f. So this is one of the obvious results because if you have x minus c factor, when you plug in x equals c, the x minus c becomes 0. Since it is a factor, the whole thing is 0. That's why you get fc equals 0. And then along with this, we can use what we call the rational roots theorem. So the rational roots theorem says if x equal p over q is a 0, so that is a possible rational 0. You know that the rational number is any number that you can write as a ratio of two integers. So that means p and q are integers. So you divide the two, then you get a rational number. So this theorem allows you to find all the rational zeros. So it says that if x equal p over q is a 0, then p has to divide the constant term. So p divides the constant term. That's how we write it. And then q divides the leading coefficient. So the p divides the constant term and q divides the leading term. So how we do the problem, once we know that, then we can write, we say p divides a naught. So then we can write all the possible values of p. So that means those are all the factors of a naught, which is going to start as plus or minus 1 and the rest of the terms. And then we do the same thing since k divides a n, Q has to be the factors of a n. That means it's again start with plus or minus and the rest. And then what we are gonna do after we know P and Q, we can write the possible values of P over Q. You can see this also going to start with plus or minus 1, and again depending on the rest of the values you can write them. So we write these are all the possible rational zeros. So this does not allow you to find irrational zeros or the complex zeros. So these are only the rational zeros. But once you know the rational zeros, then you can reduce the polynomial into a lower order. That's what we normally do. So we can see that in a problem. And after that, after we know all those P and Q values, we're going to plug in these values to the function and use the factor theorem. So plug in these values, plug in these values to fx. So that's what we do, and then see whether it's gonna make it 0. If it's gonna make it 0, that means you can find a factor. So we try to reduce one by one like that. So that's the rational rules theorem. And then so sometimes what we do after we know one factor, we can divide the original polynomial by that factor to get a reduced polynomial. So that we can do. So for that we can either use the long division or the synthetic division. We normally use the synthetic division because that's much quicker. So what is the synthetic division? So in the synthetic division, what we normally do, we only work with coefficients. That's what matters. So we can write all the coefficients of the original polynomial, so an, and then an minus 1. So if there's a term missing, you're gonna put a 0 for that. So we can write all the terms, all the coefficients in that in the order from larger to smaller. I mean the corresponding terms has to be the larger to smaller. So we'll say xn and then go to xn minus 1 like that. And then what we can do, let's say you want to check c is a 0, so we're gonna use this special diagram. So we're gonna draw two lines like that, and then we're gonna put a 0 here. So that's the 0 that you want to check whether it is a 0. So you can put it there, and then the rest of the calculation gonna go like this. So the first thing would be we're gonna copy is an down without any change. So you're gonna copy an down, and then after that we're gonna multiply by c as the multiplication step, and then we're gonna add that the product, we're gonna put it there, and then after we do that we're gonna add along this line and get a new number, and after this new number again you multiply by c and put it there, and then add along. So you just keep doing it, um, and you can see that since c is a 0, so at the end you should get a 0 here. So that 0 confirms that um, c was a 0, and also the numbers appear here bottom there are the coefficients of the quotient. So these are the coefficient of the quotient. So that means, and then also you can see that it's 1 degree less because your last term is 0, and then we can use we can again use another value to see whether that's a 0. So you just keep doing this process until you get a quadratic, cubic, or linear. Then we can stop the process there. Okay, this is what we call the synthetic division, and then the last thing is what we call the Descartes sign rule. Descartes' rule allows you to find how many positive zeros or negative zeros a polynomial has. So this is gonna give you number of zeros, number of zeros. So what it says there, so there are two cases. The first one says the number of positive zeros, is equal to the sign change. You just count how many sign changes in fx, or is less than by an even number. That means, let's say there are 4 sign changes. So then you're going to subtract even numbers. So that means 2 or 0. So that means either, so if there are 4, then 4, 2, 0. If there are 6, then 6, 4, 2, 0, like that. So if there are 3, then 3 and 1, because you subtract even numbers. That's for the positive zeros, and we have a similar one for the negative zeros. So the number of negative zeros is equal to the sign changes in f negative x. So you're going to find what is f negative x, and then you again count the sign changes. So it says it's either that number or less than by an even number. You subtract even numbers and it can give you the number of negative zeros. And why we need this can tell you that how many positive zeros or negative zeros. Then you don't want to, like, let's say for example we find 1 0. So if you find 1 0, if the Descartes rule says there's only one, then you don't want to substitute any other zero. Let's say there's a 1 positive, that means you don't want to plug in any other positive values. If there's a like 1 negative, then you only need to find this one, because we know that there are no more, so that you can save time. So this gonna allow you to find the right number, and you don't want to find any more because it says exactly how many. So that's how you use the Descartes rule. And let's see how you can use these ideas in several problems. So as a first problem, we have fx equal 2x cubed plus x squared minus 4x minus 3. So the first one, we can use the Descartes rule. um, Descartes rule. So if you want to use the Descartes rule, we're going to look at fx. So in this case, fx equal 2x cubed plus x squared minus 4x minus 3. And you can see that you can start with a plus sign. So there's only one sign change. But that's the only one you can change from plus to minus. So there's only one sign change. That means that number of positive zeros is 1. So which is number of positive zeros is 1. There's only one sign change, so one positive zero. And then again, to find the negative zeros, we can look at f negative x. So f negative x means it can change the sign of odd terms and then leave the others as it is. So that means there's an odd power, that means it's going to be negative 2x cubed. So this is a even power, so we can leave it. It's a negative, it's a odd powers change the sign, even powers do not change the sign. So this is a odd power, so we're gonna change the sign. Odd power means is x to the 1, so that's odd number. And then a negative 3, so that is f negative x. And then we're gonna start count. So it's negative to positive, there's sign change, and then positive to negative, there's a sign change. So there are two sign changes, 1 and 2. So that means number of even zeros, so number of negative zeros, is either 2 or 0, because when you subtract 2, you subtract even numbers. So when you subtract 2, you can get 0. That means there are either 2 or 0, even there are either 2 or 0 negative zeros. Yeah, so there are 1 positive 0 and 2 or 0 negative zeros. Now what we can do, we're going to find the possible values using the rational roots theorem. So next we're going to use the rational roots theorem. Some people call rational roots theorem, sometimes it's rational zeros theorem. It's the same thing. So what it says that if p over q is a 0, then p has to divide the constant term, in this case negative 3. This can give you the possible values of p. So the possible values of p has to be plus or minus 1 always, and then the other factor is plus or minus 3. So those are the only options for p. And then q again has to divide the leading term, that means 2, leading coefficient. That means q has to be again plus or minus 1 and plus or minus 2. Knowing these, then we can write the ratio of p over q. So that means the possible x values are, which is p over q, that means the ratio, that's a rational 0. So what we normally do, we're gonna keep q fixed, and then consider all the possible values of p, and then keep changing the values of q. So that means if you consider q is plus or minus 1, p over q has to be plus or minus 1, and then plus or minus 3. So that's always repeat. All the values of p repeats because of q equal plus or minus 1. And then if you consider q equal plus or minus 2, you're going to get plus or minus 1/2 and plus or minus 3/2, because you divide by 2. Okay, and then you can see that this number is always there. Plus or minus 1 is always there. So that is like kind of common value we're gonna plug in. So we're gonna plug in those. We normally start with the smallest value. We're gonna plug in those smallest values to the function and see whether you get a 0. If you get a 0, from the factor theorem, you can find the corresponding factor. So now after the rational roots theorem, we're gonna go to the factor theorem. So let's use the factor theorem now. Factor theorem. So what we're gonna do in the factor theorem, we're gonna plug in the values. So it's p. We're gonna plug in the 1 because that's the easiest. So you plug in 1, you get 2 plus 1 minus 4 minus 3, and you can see that this is not equal to 0. That means 1 is not a factor. Let's plug in negative 1, but those are the easiest value to plug in. So if you plug in negative 1, you get 2 negative 1 cube, and then you get plus negative 1 squared, and then negative 4 negative 1, and then negative 3. And then if you simplify these, you're going to get negative 2, and then plus 1, positive 4, negative 3, and you can see that this is 0. This means that x minus minus 1, that means x plus 1 is a factor. You subtract the value. So once you subtract a negative 1, it's become this is negative negative 1. It's become positive 1. Okay. So now since we know one factor and this is cubic, what we can do is we can use either log division or the synthetic division to find the quotient, because that's going to give you the other values. And also we know that there are two negative values. There are two negative zeros. So maybe the negative one repeat. But unfortunately, if there's no way you can plug in the same value to the function and get another one. So what we normally do is we can use a synthetic division and check whether the negative one is again a factor. So the easiest way to use is synthetic division. Let's see how we can use a synthetic division for that purpose. So it is the synthetic division now. Synthetic division. So what we're gonna do, we go with the coefficients. So the coefficients are 2, 1, negative 4, and negative 3. So we're gonna check whether negative 1, we already know that negative 1 is a 0. What we want to find is a quotient. So what we normally do, we copy the value down here and then multiply the two values and put it there. This is negative 2, and then when you add, you get negative 1, and then multiply the two values, you get 1, and when you add, you get negative 3, and then when you multiply, you get 3, and when you add, you get 0. So the 0 confirms that our process is correct. Now what we can do is, since this is quadratic, actually you have two ways to proceed with this. Either you factor the quadratic, that's one way to do it, or we can use a synthetic division again to check whether there's another whether the negative one is 0 again. So let's see that idea. So what we can do, we can use synthetic division again for this part. Um, so we can check negative 1 again. So that means you're going to copy the number down and multiply. So so this number is simply you copy 2 down and then multiply. So you can see 2 times negative 1 is negative 2. When you add, you get negative 3, and then multiply the two numbers, you get 3. When you add, you get 0. So that confirms that, that says that negative 1 is a factor again. And also the other thing is this is the quotient, so we get the quotient right there. So that means because of this argument, we can simply write the complete factorization, which is fx equal 2x cubed plus x squared minus 4x minus 3 equals to, you can see the first factor was x plus 1, second factor was also x plus 1, third factor is given here. The coefficients are 2x minus 3. That's coming from the those two numbers. So that is the complete factorization, which you can write as x plus 1 squared 2x minus 3, like that. So that is the complete factorization, and after we have the complete factorization, what you can do is you can set them equal and find the zeros. So this is how you can use the synthetic division to find a repeated factor. So let's see the second method. What we have is, I'm going to call this is the second method. So in the second method, what we can do, so we can we have so this is like works for cubic easily. So we have 3x cubed plus x squared minus 4x minus 3. That's what we have. But we only know one factor, which is x plus 1. And from the first synthetic division step, we know the coefficients. Our coefficients were 2, -1, -3. That means that corresponds to the quadratic function 2x squared minus x minus 3. That's the corresponding quadratic function. Now what we're going to do, we're going to factor this quadratic function. This is not that difficult to do. We're going to multiply the two numbers. So you're going to get -6, and then we're going to find two numbers uh, that when you multiply you get -6. When you add you get -1. So the two numbers are -3 and 2. It's very clear. Now we can write the factorization. So how we can write the factorization? We know there's a leading term is 2x squared. That means the terms has to be 2x and x, because those are the only factors of 2x squared. So now to find the other number, it's very simple. We're gonna look for the coefficients, and then we're gonna divide the coefficient by we can divide the number by the coefficient. So for example, this number is simply 2 divided by 2, so that means +1. And then to find the other number, what we're gonna do, we can divide -3 by 1, because in front we have 1, so that means we can divide by that. So that means it is -3 divided by 1, which is -3. So that's how you get the two numbers right there. So that's going to give you the complete factorization. Again, as before, we can write this one as x plus 1 squared, and then 2x minus 3. So that is the complete factorization. So after we have the complete factorization, what we normally do, we can set this equal to 0. So we can write this one as x plus 1 squared 2x minus 3 equals 0. This tells you that either the first factor equal to 0 or the second factor equal to 0. From the first one it says that x equal -1, or the second one it says that x equal, you move 3 to the other side and divide by 2. So those two are the two zeros you're gonna get. And then also you can see that the -1 has a multiplicity 2, so we can write it. So you can see that finally x equal -1 is a 0 with multiplicity 2, with multiplicity 2 because the power is 2 there, and x equal 3 halves is a 0, with multiplicity 1. So that's how you kind of finalize a problem like that. Okay, so let's look at the next problem. As the next problem, we have gx equal x to the 5th plus 3x to the 4th plus 3x cubed plus 9x squared minus 4x minus 12. So what we're going to do, we can use the Descartes rule first. So we can look at the gx function, so which is x 5th 3x to the 4th plus 3x cubed plus 9x squared minus 4x minus 12. And you can see the sign changes. So there's only one sign change there. So that means that's only sign change you can see. That means there's only one positive. So one positive 0. There's only one positive 0. that means later when you try to use the rational roots theorem, if you find one positive zero, and you can stop there because there are no more positive zeros. So let's look at the negative zeros. So we can look at g negative x. That means it's going to change the sign of all the odd powers terms. That means negative x to the fifth, positive 3x to the fourth, negative 3x cubed, positive 9x squared, and this is also um, uh, so it's going to be positive 4x and negative 12. So you can change the sign of odd powers. Now you can see there's sign change here. There's 1, and there's another sign change there 2, and then 3, and then 4. So there are 4 sign changes. 1, 2, 3, 4. So that means so you can see this says that the number of negative negative zeros are either 4 or 2 or 0, because we subtract 2 from 4. So that means, so you subtract even numbers from 4, so you end up with 4, 2, 0. So that means it can be either any of those numbers. There are no negative zeros, or 2 negative zeros, or 4 negative zeros. You cannot say exactly how many, but we know that there's exactly one positive zero. Now what we're going to do is we can use a rational roots theorem to figure out what are the possible zeros. Um, so we're going to go with the rational zeros theorem, or rational roots theorem. It's the same thing. Um, so we know that the p has to divide the constant term. So this says that p has to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So 12 is one of the number which has so many factors. 6 has a lot of factors. 18, 24, 36, those are all have a lot of factors. And q has to divide the leading term, which is 1. So that means q has to be only plus or minus 1. So there are no more. So that means we can write the p over q now. So the p over q has to be, since plus or minus 1, you just repeat the values of p. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So what we normally do, we use smaller values like plus or minus 4 and plus or minus 2. Those are the ones we try to use for a smaller degree polynomials. So let's try to use those values and see any of them makes it a 0. So we're going to go with the factor theorem now. So factor theorem. So we're going to plug in the easiest value, that means 1. If you plug in 1, you get 1 plus 3 plus 3 plus 9 minus 4 minus 12. Actually, this is exactly 0. That means x minus 1 is a factor according to the factor theorem. And then unfortunately, there's no way to figure out whether 1 is a repeated factor. For that, you have to divide first, and then you have to use a synthetic division, the shortcut method. Let's see whether negative 1 is also a factor. So if you plug in negative 1, you end up getting negative 1 plus 3 minus 3 plus 9 plus 4 minus 12, and you can see this also 0. So that means x plus 1 is a factor as well. Now we figure out two factors, but you can see that the original polynomial is of degree 5. So that means there are 3 more factors. There are 3 more possible factors, because there can be some complex zeros there. So the next step would be, since there are more, we can use the synthetic division now. So use the synthetic division. So if you use the synthetic division, we're gonna get, so we're gonna go with the coefficients first. So we have 1, 3, 3, and 9, -4, -12. And then we're going to check whether 1, we already know that 1 is a 0, so we're going to find the coefficient, um, the quotient. So we're going to copy 1 down and then multiply and add. So it is 1, so you get 4, and then multiply, which is 4, you get 7, multiply, which is 7, you get 16, and then you're going to multiply, you get 16, we're going to add, you get 12, when you multiply you get 12, when you add you get 0. You should get 0 because we know that 1 is a 0. Now what we can do is, so we get the quotient already, but we don't want to write the quotient. Now we can check whether, um, and we already know that the -1 is a 0, that means the -1 has to be a 0 of the quotient as well. So because of that, what we can, instead of dividing by 1, we're going to divide by -1, because we know that the -1 is also 0. So let's repeat the process again. So copy down 1 and then multiply, so you get -1, add, you get 3, multiply, -3, add, you get 4, multiply, you get -4, add, you get 12, and then -12 and 0. So it should happen and happen. So that means now we get the new quotient. Now we can check whether, for example, -1 is again a factor. So you can check that, or 1. So let's say, like, because we don't know, let's check whether -1 is a factor again. Start with the -1, and then again copy the number down, multiply and add, and then multiply and add, multiply and add, and you can see that you're going to get 10. So which is not equal to 0. Since this is not equal to 0, this cannot be a 0. That means -1 is not a repeated factor. That's what we learned. Because it's not 0, so this is not equal to 0. That means this is not a 0. So not 0, not a 0. So not a 0. So that's what we learned here. Okay, good. So that means -1 is not a repeated factor, but we found two factors. So now what we can do is, since you know the two factors and we also know the new quotient, these are the coefficient of the quotient, we can write what we have now. So so we can write using these coefficients. So we can write this. So we have gx. We have gx, which is equals to, we know x minus 1 is one factor, x plus 1 is another factor, and then we can write the quotient now, which is x3 plus 3x squared plus 4x plus 12. Actually, we could have used the synthetic division again with other possible numbers, because we know there are a lot of other numbers from the rational root theorem, and we can use those values. I mean, it's time consuming, but we can try that. This exhaustive argument, we just try all those values and they should work. But we're gonna find a different argument here. What we can do, you can see that this is a cubic. Since this is cubic, we can use the command method for cubic. The command method for cubic is the grouping method. So we're going to try the grouping method, because since this is a cubic polynomial. So try grouping method. That's like a command method for cubic when you see a cubic one. So we're going to do that. So that means we have what we have. We have x3 plus 3x squared plus 4x plus 12. So we can use the grouping. That means we can group the first two and the next two. So you can see from the first two, you can pick x squared. You can take x squared as a factor. So you get x plus 3. So the goal is to create x plus 3 term from the other two. So you can see, you can, if you pull f4 out, you get exactly the x plus 3. So these two should match. If they don't match, you can use the grouping technique. Since this is match, we're going to pull that as a factor. and then we have x squared from the first term and the plus 4 from the second term. So that goes there and that goes there. Good. That's going to give you the complete factorization. So now we can write gx like this. So we have x minus 1, x plus 1, x plus 3, and x squared plus 4. Now what we're going to do, we're going to set this equal to 0 because we are looking for zeros. So for zeros. So each factor set equal to 0. So this says that x minus 1 equals 0, or x plus 1 equals 0, or x plus 3 equals 0, or finally x squared plus 4 equals 0. So the first three going to give you zeros, but for the last one we can do is x squared you can write as negative 4, and then we can write as 4 times I squared, the complex number. We can use that, and then we can take the square root. Now once you take the square root, what will happen, because of the even power you will get plus or minus. 4 gonna give you 2, I squared gonna give I. So those are two complex zeros, and then we have other real zeros here. So we're gonna because since they are looking for the real zeros, we can actually ignore this solution, because we know that for any real numbers this cannot happen. So we can ignore this. If you need only the real zeros, so this factor you can ignore because there are no real zeros for that. So only real zeros are 0, 1, -1, and 3. So you can say the real zeros, because we are looking for real zeros. So the real zeros are x equal plus or minus 1 and -3. Because we know that if it is a real number, x squared plus 4 cannot be equal to 0, because for real numbers x squared is always greater than or equal to 0. For real x squared is greater than or equal to 0, so therefore x squared plus 4 is greater than 0. That means it can never be equal to 0 for real values. But if you want to do this in complex domain, yes, you can find values, but for real you cannot simplify this further than that. Yeah, so if you want the real zeros you can stop there, but if you want complex zeros you can go to the next level and find them, but we can do that later. Okay, so that's how you find the real zeros of the second polynomial. So let's do the last one of this type. So for the next one, we have hx equal 2x to the fourth minus 5x cubed minus 14x squared plus 5x plus 12. So we can use the same method. So we're gonna you know that the Descartes theorem is like kind of optional, because it's gonna give you uh, it, it can help you save time, because what we normally happen, if you don't know how many zeros are there, you just keep plugging. But the Descartes theorem says how many you have. So even in the previous problem you can see that there was only one positive zero, and then after you find one positive zero you are not going to find any more positive zeros, because that's why you did not plug in one again for the problem. But we try to plug in -1 again, because we don't know whether -1 was a repeated zero. That was the reason why you plug in -1 again. So the Descartes theorem help you like that, but you know that's sometimes optional. You can just go with the rational zeros theorem, and then you can plug in them and try to find the quotient. So that's kind of like common way to do it. So let's try to use that and see how it works. So what we normally start with is x equal p over q is a 0. Then we know that the p divides the constant, so which is 12. That means p equal plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Q divides 2, that means Q have only few options, is be plus or minus 1 and plus or minus 2. So then P over Q has these options, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. That's from using 1 for Q. If you use 2 for Q, you're going to get plus or minus 1 half. And then if you use 2, you get 1. You get if you use 3, you get plus or minus 3 halves for P. And then you get plus or minus 2, plus or minus 3, and plus or minus 6. So the other values just repeat. So we normally start with the easiest values. That's what we normally do. And if that didn't work, then you try plus or minus 2, and then if that didn't also work, we're going to go plus or minus 3. So we go one by one like that. So let's plug in the values now. So we're going to plug in 1. So if you plug in 1, you're going to get 2 minus 5 minus 14 plus 5 plus 12, and you can see that which is a 0. So that means this says that uh, x minus 1 is a factor, and then again we plug in -1, that's the other smallest value, and you can see that 2 plus 5 minus 14 minus 5 plus 12, and you can see this is also 0. That means x plus 1 is a factor. Good, we found two factors, and since this is degree 4, there are two more factors. So what we can do is we can use the synthetic division to find the other factor. So we're going to go with the synthetic division now. So we're going to go with the constants. So we have 2, -5, -14, 5, and 12. So so we're going to check, we can use 1 first. So if you use 1, you can see you're going to get, so which is 2. So you get 2, so you get -3, and then -3, so you get -17, and then -17, you get a -12, and then -12, which is 0, so that means it worked. And then again, we also know -1 is a 0, so we can use a -1. So if you use -1, so you're gonna get 2, and then -2, which is -5, and then +5, which is -12, and then 12, which is 0. So that means we get the coefficients of the quotient. So we can write, using that idea, we can write the third term. So we can say hx equals to x minus 1, x plus 1, and the other term is 2x squared minus 5x minus 12. Those are the coefficients we get, and then we can use the factoring argument. So what we can do, you know that your number is 2 times -12, that means -24. So we are looking for two numbers. When you multiply, you get -24. When you add -5, that means -8 and 3 works. Those are two numbers, and then we can easily find the factorization. So it is x minus 1, x plus 1. So we again know that one has to be 2x, the other one has to be x. So so to find this number, you're going to divide -8 by 2, because you cannot divide 3. That's why we pick that. So that means which is -4, and then to find the other number, we can divide 3 by 1, so which is plus 3, 3 by 1. Okay, so that's going to give you the complete factorization. Since we are looking for real zeros, you can see these are all linear, so we're going to get real zeros. So we're gonna set this equal to 0, and then because of that, then you can see that x minus 1 equals 0, or x plus 1 equals 0, or 2x plus 3 equals 0, or x minus 4 equals 0. So that means x equal plus or minus 1, and then 4, or finally you get negative 3 over 2. So those are the 4 zeros of these polynomial. So it is not that difficult, and you can easily find the two numbers, 4 numbers. Good. I want to show you another special quadratic equation, like how to factor this. Like for example, so I'm going to say important. So let's say we have, for example, 4x squared minus 13x minus 12. So you can see the number here is, you multiply those two, you get 4 times negative 12 means negative 48. So yeah, I'm gonna write it here. So it's negative 48. So what you're looking for is when you multiply, you get negative 48. So that means you need to for two factors of negative 48 that's added up to negative 13. So the two factors are negative 16 and 3. So you can see those two factors added up to negative 13, and multiply, you get negative 48. Now the question, what are the factors? So you can see that now the number is 4. If the number is 4, you can write 4 as the 4 times 1 or 2 times 2. So let's see which one work. Let's say, for example, you try to find 2x factorization, and you can see that if you pick 2x, the 2 doesn't work, doesn't divide 3 evenly. So since 2 doesn't divide 3 evenly, we are not gonna pick this option as a factorization, because it's not like it doesn't divide even. So that means we're gonna ignore this one. We're gonna go for the other one. What's the other one? 4 times 1, so that means 4x and 1x, like that. So that means you can find the factorization. How to find it? So the number is 4, so when you divide, you're gonna get negative 16 over 4. That means negative 4 goes there, and the other number is, it is coefficient is 1, so this one is 1 over 3. So the other number is 3 divided by 1, that means plus 3. So those are the factorization. So that means it's gonna work, but you have to consider some cases. I like if you get a number like a 4, but if you have two, like if you have prime numbers, these are easy to do, like 2, 3, 5, 7, things like that. But if you get numbers like 4, 6, you have to consider several cases, and until you get the right one. But this is still easy to find the factors using this way. So it's just a division there. Okay, so that's about that. So let's try to go to the next type. What we're trying to do now is we're going to find complex zeros. Uh, so the question is, find complex zeros. Complex zeros of a polynomial. Complex zeros of a polynomial. Find complex zeros of a polynomial. So let's talk about theories. So there are certain theories involved with complex zeros. So one is that so the first one says that any real polynomial is a real polynomial. Any real polynomial. What's a real polynomial? Real polynomial is polynomial with real coefficients. So any real polynomial can be factored into linear or irreducible quadratic factors. So any polynomial, if you get, you can bring it down to linear factors or irreducible quadratic factors. That means there are quadratic, you can break into any more linear factors using with real zeros. For example, you're going to get factors like x squared plus 4. So if you have x squared plus 4, you know that there are no more real zeros. There are complex zeros, but no more real zeros. That's what we call irreducible quadratic factor, like something like x squared plus 4. X squared minus 4 you can, but x squared plus 4 you cannot. Okay, that's first one. And then also another one. Um, so if you have a cubic polynomial, we normally try the grouping method. So that's like another trick, I should say. So if it is cubic, try a grouping method. Try grouping method. So this is a kind of trick that we use for cubic. Use the grouping method. Um, good. So those are some of the things that we're gonna use when you try to find complex zeros of a real polynomial. So in this case, we assume that this is a real polynomial, not a complex polynomial. So let's look at the first example. Before that, I also want to recall some of those important factorizations. For example, the difference of squares. We have x squared minus y squared, which is x minus y and x plus y. And then also we have identity for cubes. Like for example, if we have x cube minus y cube, so we have x cube minus y cube, which is very similar, is x minus y. That's the first factor. The second factor is x squared plus xy. If you minus, you can plus, and then y squared. So you can see this plus term there. There's no 2. And then also we have x3 plus y3. So what's going to happen is x plus y, so it's going to follow the pattern of the term, and then opposite signs x squared minus xy. This is a plus, then become minus, and then this is also plus. So only special term is this term. Good. So those special factorization can help you when you have problems like that. So one for the difference of squared, the other one is for difference and sum of cubes. Okay. So this is for the squares. These two for cubes. Good. So let's look at the problem now. The problem says find the complex zeros of the polynomial. So when you want to find the complex zeros, we again use the exact same idea that we use for finding real solutions. Only difference is this time we can completely factor it into linear factors because we are looking for complex zeros. But if you are looking for only the real zeros, sometimes it's gonna end up with linear or quadratic irreducible. But if you get irreducible, you can even continue further and break it down to complex zeros. So you can see the difference here. And also you can see that the first one is a cubic polynomial. So if you have a cubic polynomial, sometimes we can use the grouping method, especially when you have 4 terms. When you have 4 terms, you can see there are 4 terms here. We can try the grouping method for these problems. And also you may notice that these 2 terms are not in the right order, because like it's not in a standard form. So what we're trying to do first, we can write them in standard form, so which is x3, and we're going to bring this term here, so 2x squared, and then plus 13x minus 26. If you do not do that, it's going to cause errors. Now what we can do, we can use a grouping method. You can see these 2 groups, you can group them. From the first group, you can pull out x squared, so you're gonna get x minus 2. From the second group, you can see that to get x minus 2, that's the goal, to get the same term. You can see you can pull out 13. If you pull out 13, you will get x minus 2. Now these 2 terms are the same, so we can write the common term, which is x minus 2, and then the other term is x squared plus 13. So those two terms, one coming from here and the other one coming from there. So those are the two terms. And so this is a complete factorization, but you can see we are looking for complex. So the second one is the irreducible quadratic. But we're going to continue further. And after that we can say, so which we said this equal to 0 because we are looking for zeros. So you can see that x minus 2 equals 0 or x squared plus 13 equals 0. The second one you can rewrite as x squared equal negative 13. So when you do that, we know that what we're going to do now, we're going to write this one as 13i squared. So once you write this as 13i squared, when you can take the square root, so so this is going to lead to x equal, since it's an even power, so you can see that this is a plus or minus. We take the square root of the number, which is 13, and then I squared become I. So that is the complex zeros, and the real zero is x equal 2. So those are all the zeros that we need. So that means the zeros are you can see x equal 2 or plus or minus square root 13 I. So that's the solution for this problem. So we have gx equal x to the fifth plus 3 x to the fourth plus 3x cubed plus 9x squared minus 4x minus 12. Um, so we can directly, because we know that if you use a rational root theorem, plus or minus 1 is always an option. So that means we can try them directly. So let's say g1. So you plug in 1, you're going to get 1 plus 3 plus 3 plus 9 minus 4 minus 12, and you can see this is 0. That means x minus 1 is a factor. And then again we're going to try g minus 1 also. So if you plug in minus, it's going to change the sign of odd terms. That means negative 1 plus 3 minus 3 plus 9 plus 4 minus 12, and you can see this is also 0. That means x plus 1 is a factor. So since we have those two factors, we can use the division to find the quotient as before. So we have 1, 3, 3, 9, negative 4 and negative 12. Since 1 is a factor, so it's 1, so you get 1 1, so 1, so you get 4 and then 4 and then 7, so you get 7, so you get 16, and then 16, so which is 12, so it's 12 and 0. And then since negative 1 is a factor, so we can continue the process. So 1, so you get negative 1, so 3 and then negative 3, so 4, negative 4, so which is 12, and negative 12, which is 0. And then so we have the quotient here, so we can write gx like this. So gx is, we already have x minus 1 and we have x plus 1, and the other factor is there are 4 terms, that means it has to be a cubic. So it is x3 plus 3x squared plus 4x plus 12. Now what we can do, we're going to factor the last one using the grouping method because it is a cubic one. So we can say now consider if it is a logical argument, so it is x3 plus 3x squared plus 4x plus 12. So we're gonna group these two and those two, so we're gonna have x squared from the first one, which is x plus 3, and then your goal is to get x plus 3. That means you're gonna pull 4 out, so you're gonna get x squared plus 3. You're gonna pull a 4 out, so you get x plus 3. You get x plus 3. So write the common factor, which is x plus 3. From the first one you get x squared, from the second one you get 4. So you write these two terms here. Good. So that's the complete factorization. So then because of that, then we can write gx which is x plus 1, x minus 1, x plus 3, x squared plus 4. And then now these are complex. That means anything can happen now. And you can see that this is the complete factorization in the reals, either to linear or quadratic, irreducible quadratic. So these are the linear factors, and that is the irreducible quadratic factor. But in complex, you can even simplify this further. Uh, so, so what you can do is we're gonna set this each factor equals 0. So you're gonna get x plus 1 equal to 0, or x minus 1 equal to 0, or x plus 3 equal to 0, or finally x squared plus 4 equal to 0. Since this is complex, now this is a valid one. So what we can do is x squared equal negative 4. This one you write as 4 times I squared. So that means x has to be plus or minus, because the even power there are 2. So 2i. So that is the complex 0. And then we can write all the zeros. So this says x equal negative 1. This is x equal 1. And this is x equal negative 3. So if you combine all of them, so the zeros are uh, x equal plus or minus 1, negative 3, and plus or minus 2i. So these are all the 5 zeros we have, because n degree polynomial has n zeros in the complex domain. So n degree polynomial has n zeros in complex domain. So since this is a degree 5 polynomial, there should be 5 zeros, and we found all those zeros. Okay. Let's talk about a few further properties of complex zeros of a real polynomial. So there are a few things that to focus on. We talk about complex zeros of a real polynomial. The polynomial has to be real. Real polynomial means polynomials with real coefficients. All the coefficients are real numbers. So, so the first one is the degree n polynomial has n complex zeros. So this is a very interesting result. So if the polynomial has n degree, that means there should be n complex zeros always. But this does not work with real zeros. So that means you cannot say that there are n real zeros of a real polynomial, but there are n complex zeros of a real polynomial. That works, but not for real zeros. Okay, so the next one is the factor theorem. We still use the factor theorem. So that means if fc equals 0, if and only if x minus c is a factor, so we can use a factor theorem again. And then also there's a very interesting result, and which is what we call the conjugate pairs theorem. So it says that if a plus bi, so b can be negative, so we just consider a plus bi, because if b negative, this is like a minus bi. So what it says that if a plus bi is a 0 of a polynomial with real coefficients, this is very important. The polynomial should have only real coefficients. If this is the case, then a minus bi, which is what we normally call the conjugate, is also a 0. So it says that if a plus bi is a 0, then a minus bi should be a 0. So those are called the conjugates. So that means the zeros appears as conjugate pairs in real polynomials. So the zeros appears as conjugate pairs in real polynomials, all the complex zeros. It doesn't work for real zeros. It only works for complex zeros. The polynomial has to be real polynomial. If the polynomial is real, the zeros appears as conjugate pairs. So let's try to look at a problem. So what it says, find a real polynomial find a real polynomial of least degree. Why we say least degree? Because you can always multiply by a you can increase the multiplicity, so that's why we say least degree, because even if you increase the multiplicity, it doesn't change those zeros, so that's why we say least degree. That has the following zeros. So these are the zeros. They're asking, can you find the polynomial? So there's a basic theory. So what's the basic theory? It's a factor theorem, because we know that if c is a zero, then x minus c is a factor. So we can use that idea to solve problems like that. So let's start with the first one. So first one says, so we have zeros. Zeros are 1 and -5. So that means according to the factor theorem, so the corresponding factor should be x minus a, that's the first zero, x minus b, that's the second zero. A and b are zeros. So we're going to plug in for a and b 1 and -5. So that means it's going to be x minus 1. This is x minus -5 because -5. And then what happened, this is x minus 1, this is x plus 5, and then we can distribute. Once we distribute, we're gonna get we're gonna multiply x with x, so you get x squared, and x with plus 5 on the other side, and the x with the -1 on the other side, and then -1 times 5 is -5. Once you simplify, you get you can see that you can combine these two, so you get x squared plus 4x minus 5 has 1 and -5 as zeros. It's a very simple idea. So we can continue that even with 3 zeros. Let's look at part B. So in part B, we have 3 zeros. So we have zeros 1 and plus or minus 3. So we can use the same idea. So we can write this one as x minus 1 because 1 is a 0, and x minus 3 because 3 is a 0, and x plus 3 because minus 3 is a 0. Okay, now what we can do is we can combine these two first, because we know that if we have x squared minus y squared, which is simply x minus y, x plus y. So this is what we have now. So we have this. That means we can go backward. So that means we can write this one as x minus 1. You square the first one minus square the second one. So it's 3 squared. That's what you get from the formula. So formula directly give you that. Now we can simplify this. So we have x minus 1, x squared minus 9. Now we are going to distribute. So you're going to get x times x squared, you get x cubed. Now think about how to get the x squared term. To get x squared term, the only way that you can do is you have to multiply -1 with x squared. That's the only way. That means negative x squared. There are no x squared terms here. And how to get an x term? You have to multiply the other x with -9. That means -9x. And then at the end, you're going to multiply the numbers. You're going to get 1 times -1 times -1, which is 9. So that is the polynomial you are talking about. That polynomial has 1 and plus or minus 3 as zeros. Okay, let's go to part C. So part C says that the zeros are 2 and 3 minus I. Now you can see this is a complex number. Since this is a complex number, we can use the conjugate pairs theorem. So since the polynomial is a real polynomial and 3 minus I is a complex zero, 3 plus I is also a 0 by conjugate pairs theorem. Okay, that means we know all three zeros. So this one automatically comes because x 3 minus I is 0. Since we know the zeros, now we can do the same thing. We're going to multiply them to get the polynomial. And also one last thing, you can always multiply this polynomial by a constant. So that's because we don't know the actual polynomial, you can always multiply by a constant. But since we are looking for just one polynomial, you can just write it like that. Otherwise, we normally multiply that by a constant in front. Good. So, so let's finalize the problem. So we have hx. Let's call hx. So which is x minus 2 because that's a 2 is of 0, and then we have x minus the first complex number which is 3 minus I, and then x minus the second complex number which is 3 plus I. Now we just treat these as constants or numbers, and then we can write it like this. If so we leave the first term as it is for the moment. So what's going to happen here is, and you can see that you multiply x with x, so you multiply x with x, so you get x squared, and then you're going to multiply x with that term. So when you multiply x with that term, you can see you can pull the negative sign out, so you're going to get x times 3 plus I. And you can do the same thing with the other terms. You can see you can multiply this x with 3 minus I, so that means you can again pull the negative x out. So if you do that, you end up getting 3 minus I, so you combine like that, and then finally you get from the last two terms negative negative positive, you have 3 minus I and 3 plus I. So we can do some simplification here. First thing we notice is get cancelled. This always happen for real polynomials. And then you can also see that this is the difference of squares formula. So this can be 9, which is 3 squared minus I squared from the difference of squares formula, which is 9 plus 1. So it's going to be 10. So because of that, you can write this one as x minus 2 x squared minus, and you can see this is 336, so minus 6x plus 10. So that's what happened. And then we can distribute. So you can see you're going to get x3 minus 8x squared plus 22x minus 20 as the polynomial which has those two complex numbers as zeros, but actually there are two complex numbers and one real as zeros. So that's how you use the conjugate pairs theorem to solve a problem like that. So in general, we're gonna write like this. So you say in general, we can write a polynomial like, let's say, with a constant and which has a as a 0 and b as a 0, like that. So those are the zeros, but we multiply by a constant in front. So the reason is we don't know whether there was a constant, because which still give you the least degree polynomial. So k is just a constant, and then how to find k? To find k, we need some other information. We plug in the x value and set it equal to the given y value and solve for k. That we can do. Okay, so let's talk about the rational functions. In this problem, we are going to find the domain and asymptotes of rational functions. So rational function is when you divide two polynomials, you get a rational function. So there are several cases to consider when you find the domain and asymptotes. For example, when you want to find the domain, we are not gonna we are not gonna cancel common factors when you find the domain. But when you find the vertical asymptote, we cancel common factors. So there are certain theories like that, and also sometimes we have to divide. You have to use the either long division or synthetic division to find the oblique asymptote. So let's talk about this the theories behind that. So in this we can talk about rational functions. So under rational functions we can talk about three things. But we can talk about the domain and this, and then asymptotes. In asymptotes we can talk about vertical asymptotes and horizontal asymptotes, and also we can talk about oblique asymptotes. So let's talk about one by one. First, what is a rational function? So rational function means a function which is the quotient between two polynomials, so px and qx, and these two are polynomials. So let's talk about the domain first. So domain. So when you talk about domain, you need to, because since we divide two polynomials, we want to make sure that you don't divide by 0. So that means what we're going to do, it is any x such that the qx function not equal to 0. So what we can do, we first find the zeros and we remove them from the original domain, because we know that the polynomial has all real numbers as the domain. But what we can do now, we can remove zeros from the denominator function. That's how you find the domain. And then let's talk about asymptotes. So under asymptotes, there are two types of asymptotes. The first one is the vertical asymptote. That's the easy one. So vertical asymptote. So if you want to find the vertical asymptote, what we're going to do first, we're going to write Rx in the lowest terms. So we're going to find the common factors and remove them. So I'm going to say it's like that. So that's the simplified version. So what we normally call the simplified version. Simplified version. So from the simplified version, whatever the leftover function, the factors in the denominator are going to give you the vertical asymptote. So the linear factors of q naught x gives a vertical asymptotes. So you simplify first. That means you find the common factors and cancel them, and then the denominator gives the vertical asymptotes. So let's talk about how to get the horizontal asymptote. That has like a long process. This for horizontal asymptote, horizontal or oblique asymptote, both. Oblique sometimes we also call slant asymptote. So let's look at the polynomial or the rational function. We can write the rational function as an xn like that, and then the bm xm like that. That's the leading term. I'm also going to call this as px over qx. So there are four cases to consider. So what happens if n is smaller than m? That means m is the denominator degree is bigger than the degree of the numerator. In that case, y equals 0, which is a horizontal line. Y equals 0 is a horizontal asymptote. Case B, if the two degrees are equal and equal m, then what we can do, the ratio between the leading terms, when you divide, you can see x term get cancelled out, you get an over bm, or in this case bn, is a horizontal asymptote. You just divide the two leading coefficients. And then part C, if n is exactly one more than the degree of the denominator. N is exactly one more than the degree of the denominator. Then what happened? Then y equal ax plus b. This is the quotient when you divide px by qx, uh, which is the quotient, when px is divided by qx. Uh, is an oblique asymptote. So it's going to be an oblique asymptote in this case. And part D, if n is more than m plus 1, there are no linear asymptote. There are no linear asymptote. It can be higher degree one, but there are no linear asymptotes. So that's the theory. And then when you do a problem like that, we always use factorization. So we use the factorizations. So need to factor. When you want to find the domain and the vertical asymptotes, and not for the horizontal asymptote. Okay, so let's look at some problems now. So we have as the first one, so we have y equal 2x squared plus 7x minus 4 divided by x squared minus x minus 2. So let's look at the factorization, because that we need later. First we can see you have negative 8 and the two numbers are 8 and negative 1. So that's going to give you the so the two factors are, one is 2x, the other one is x. So 2 divided by 8 divided by 2, so that means plus 4. Negative 1 divided by 1, that means negative 1. So this is a factoring of the numerator. So you're going to get 2x minus 1 x plus 4. That's the factoring of the numerator. And the factors of the denominator is easy. So you can see it is x minus 2 x plus 1. So and then there are no common factors. Okay, so no common factors to cancel. Okay, so let's go with the domain. And when you want to find the domain, we are not going to cancel the common factors because it only comes from the original denominator. So that means we're going to go for x such that qx not equal to 0. And then so you know the two zeros are negative 1 and 2, so that means this is equals to x such that the two zeros are, one zero is 2, the other zero is negative 1. So we're going to say x not equal to 2 or negative 1. So those are that's the domain. And then let's go with the vertical asymptote. Vertical asymptote. So that for that this is in the lowest term or simplified form. That means you can look for just the factors from the denominator. So which are x equal 2 and x equal negative 1 vertical asymptotes. and go for the horizontal asymptote. And for the horizontal asymptote, you just need to look at the leading terms and which have the same number. That means the ratio is going to give you the horizontal asymptote. So that means, so you can see n equal m equal 2. So therefore, y equal a n over b m, in this case 2 over 1, which is 2, is a horizontal asymptote. And then you can see no, because you're asking all, so no oblique asymptote, oblique or slant asymptote. Good. So let's go to the next one. So we have y equal x squared minus 3x over x squared plus x minus 12, and which has factors. You can see x is a common factor, so you get x minus 3, and from the bottom you're gonna get x plus 4 and x minus 3. Those are factors, and we are not going to find the we are not going to cancel until you find the domain. For the domain you are not going to cancel, so it says x equal, so that means it cannot be negative 4 to avoid dividing by 0. X cannot be equal to 3, so that means we can write the domain now. So the domain is x such that x not equal to negative 4 or x not equal to 3. That's the domain. Now to find the vertical asymptote, what we're gonna do, we're gonna cancel. So we're gonna look for the factored version first. So this is the factored version, and then what we're gonna do, we're gonna cancel the common factor. So that means the simplified form is x over x plus 4. So the factors in the simplified factors from the bottom from the simplified form are the vertical asymptote. So so this says that x equal negative 4 is a vertical asymptote. Okay, and then for the horizontal asymptote, again you're going to look the numbers and you can see for that you can either look for the simplified version or the original version, it doesn't matter. And if you go to original version, you can see n equal m equal 2, so that means y equal a n over b m, that means 1 over 1, which is 1, is a horizontal asymptote. And you can see no slant asymptote. Good. So let's go to the next one. So we have C. We have y equal x squared minus 3x minus 4 divided by x plus 2, and which can be factored as x minus 4 and x plus 1, and the bottom x plus 2. There are no common factors, so the domain is easy, so which is simply x such that x not equal to negative 2, and then we have the vertical asymptote. That means x equal negative 2 is a vertical asymptote. And for the horizontal asymptote, and you can see there are no horizontal asymptote, but there's a slant asymptote in this case, because you can see n equal 2, m equal 1. That means n is exactly m plus 1, so that means there is an oblique asymptote. Oblique asymptote. There are no horizontal one. To find that, what we're gonna do, we're gonna do the division. And for example, if you do use the lone division, and you will So the goal is to like you want to divide the two. So x squared minus 3x minus 4 divided by x plus 2. What we normally do, we can use a synthetic division. That's much faster. So if you use that, you're going to 1, -3, -4 divided by, you put the 0 here. 0 is -2 because plus 2 means -2, and then 1 goes there. Multiply, you get -2, add -5, and then multiply, you get 10, add, you get 6. So that is the quotient. So that means it is x minus 5 plus 6 was the remainder. So we write the remainder divided by the divisor x plus 2. So we write it like that, and that's gonna give you the oblique asymptote. So you can say y equal x minus 5 is an slant asymptote. Good. And also you can use the log division to get the same answer. Uh, so for example, so if you use the log division to get the same answer, so you have x squared minus 3x minus 4. So you divide this one by x plus 2. You can see x is missing. So you multiply by x, you get x squared plus 2x, and you can subtract. Subtract means change the sign of the bottom one and add. So if you change the sign and add, you get negative 5x, and then bring 4 down here, and then missing number is -5, so multiply by -5, you get -5x, and then -10, again change the sign and add. When you change the sign and add, you get 6. You can see that you get the same answer. So this is the quotient we are looking for. Good. So let's look at the last part of this problem. So we have y equal 4x cubed plus 6x minus 9 over 5x minus 2, and it's very clear that you cannot have a 5x minus 2 factor in the denominator because the number 5, which is not a factor of 4 or -9. So that means this is a simplified form. So we can write the domain. So the domain is simply x such that, as you can see, you can find the 0 first. So to find the 0, you have 5x minus 2 equals 0. This says that x equal, you move 5 and move 2 and divide by 5. So now this says that, so that's a 0. That means x not equal to 2/5. So that's domain, and then vertical asymptote, that's easy. So the vertical asymptote is x equal to 2/5. That's going to get the vertical asymptote. That's where the that's what the that makes the denominator 0. So is an vertical asymptote, and then the further so there are, and you can see for the horizontal asymptote case, you can see n equal 3 and m equal 1. So that means n greater than m plus 1. So you can see no horizontal asymptote or slant asymptote. Okay, so that's about domains, vertical asymptote, horizontal asymptotes, and slant asymptote. Next, we can talk about some transformation techniques for certain graphs. So we can discuss how to graph certain rational functions. So we can talk about two special cases. So the first one is y equal 1 over x. So we know that y equal 1 over x has a graph like this. So it is there's asymptote there, and then also asymptote there. So there are 0 x equals 0 is a horizontal asymptote, y equals 0 is a vertical asymptote. And then there's another graph. We have y equal 1 over x squared. So this one has this special form, so which is x equals 0 is a vertical asymptote, and also x equals 0 is a horizontal asymptote, and y equals 0 is a vertical asymptote. But since we have x squared, which is positive, uh, and x squared is even power, so because x squared is even, so you get a symmetric graph. So the graph gonna look like this. So we have graph like that because of the even power here. The even power, so it has to be symmetric, and then gonna go like that. So those are the two basic graphs, um, and we can use these two graphs to find the graph of these three. So let's start with the first one. So we have x equal 5 over x minus 2 plus 3. So we're going to go step by step. We're going to start with y equal 1 over x. That's the first graph. And then we have y equal 1 over x minus 2. That's the second one. And then we have y equal 5 over x minus 2. That's the third one. And then we have y equal 5 over x minus 2 plus 3. So we're going to go with these four steps. So we start with the first one, that is the basic graph or the standard function that we already know. It looks like that, and this is what we normally call the rectangular hyperbola with a 0 there. And then in the next one, what's going to happen is going to move to the right by 2 units. So it's the same graph. You simply move to the right by 2 units. That means this asymptote gonna move to 2 now. So that means the new graph gonna look like that and this. And we can also find this intercept, which is -1/2. Just plug in x equals 0 into the corresponding function. And then what's gonna happen? It's gonna scale by 5 now. So that means the new graph gonna look like this. It's just a scaling one, so no change to the vertical asymptote. It's gonna just a scaling, so it's gonna be 5 times as the original one. So this be 5 times. It's gonna go like that. So only thing change is the you can see this asymptote y-intercept changes now. It's 5 times than the original one. So this is -5/2. And then finally, what you can do, you can lift this by 3 units, lift up by 3 units. So that means so you're gonna get a graph like that. So this is the asymptote. So the asymptote gonna move now 3 units, and this is the horizontal asymptote that you had earlier. So that means so when you move, we have -5/2, and when you add 3, it's gonna be half. So that means so new graph gonna go like this now. So asymptote moves, uh, and this is the other asymptote. Okay, so and this is 2, and this is 3. This is 0. So this is the x-axis, and this is the y-axis, and that's the final graph. So you can see that you can easily use the transformations to get graphs like that. So let's look at the next one. So we have gx equal 3 minus 2 over x plus 5 squared. Again, we're going to go step by step. We're going to start with y equal 1 over x squared basic graph. And then we're going to use the shifting. So y equal 1 over x plus 5 squared. And then we're going to go with the scaling. Y equal 2 over x plus 5. And then also we can do a flip. So put the negative sign, gonna flip about the x-axis. And then finally is a horizontal shift, which is 3 minus 2 over x plus 5 squared. So let's go one by one now. As before, So we have one of x squared graph, that is one of the basic graph, gonna go like this and go like that. Those are all asymptote, and we have a 0 here. And then what we're gonna do is gonna move to the left by 5 units. So that means so it's gonna move to left by 5 units. That means that's the new axis, so which is at -5, and then the graph gonna go like this, and then also gonna go like that. Those are the asymptotes. So that's move to the left by 5, and then now we can scale. And when you do scaling, there are two things. One is scale by 2, and also flip about the x-axis because the negative sign. That means your new graph going to look like so that's the old axis. That's the y-axis. So -5 stays at -5. I'm gonna flip. So that means so it's gonna flip about the x-axis, gonna go like that, and this one gonna go like that. Good. And also you can find what is this number. So this number is -2 25th, and this is -5, and this is the y-axis, that's the x-axis. And then now finally what we're gonna do, we're gonna lift this up by 3. So so you're gonna get a graph like that, but now you're gonna lift it by 3 units, so that's 3 right there, and then this is -5. So this is -5, and this is 3. So that means and then also you to find what is the number, what is the y-intercept, and y-intercept is 73 over 25, which is a positive number. So that means asymptote moves now, so it's going to go like that, and then and also on the other side it's going to go like this. So that's the final graph, and the new asymptote is at 73 over 25, which is little less than 3. Good. So that is the final graph. So let's do the last part. So we have hx equal 5x minus 7 over x plus 3. Here I'm going to use a special division technique. So what we're going to do, I'm going to rewrite the bottom function in the numerator. So for example, what I can do, I'm going to write 5 instead of x, I'm going to write x plus 3. But when you do that, what's going to happen, you are subtracting this product 3 times 5, because you are adding that, I mean you have to subtract that. So that means it's -7, -15 over x plus 3. So you can see the top now becomes 5 times x plus 3 minus 22 divided by x plus 3, which you can write as 5 minus 22 over x plus 3. You can get the same answer also using either synthetic division or the long division, but this is much quicker. Just use the simple algebra. Okay, good. After that, you can see this problem is very much like the first problem, first part. So we again go with this step by step. So we're gonna go with 1 over x, that is what is most close related to, and then y equal 1 over x plus 3, and then y equal -22 over x plus 3, and then finally 5 minus 22 over x plus 3. So we can start with 1 over x, that's the easy one. So we have this and that with 0 here, and then shift to the left by 3. So So the new x is -3. So new graph is going like that and going like this. So -3, and also you can find this is 1/3 if you need asymptote. And then also the next one is gonna flip over and scale by 22. So flip over and scale. So that means this graph gonna jump to this side and that one on that side. The 0 stays there. Actually, that's not exactly correct because we have the asymptote. So I'm going to erase this one. So you can see, so we have this, the y-axis, and we need vertical asymptote. So now we have, we can flip over. So when you flip over, it's gonna go like that now, and that's that one. So this is -3, and then you can see this number is now multiplied by -20, so it's -22/3. So this is little smaller than -7. Okay, now what we're gonna do is we're gonna add 5 here. So that means because this is little smaller than -7, when you add 5, it's still negative. So that's what we can get from that. So so that's the axis. So this is at -3, no change, and the new axis is at 5, not to scale. So this is 5, this is -3. You can see this is still negative. So it's gonna go like that because it's still negative. And then so this one is going over there between those two asymptotes. Okay, so this is the y-axis and that is the x-axis, and this is negative. So you're gonna add 5, so you're gonna get -7/3. Okay, so that is the graph of the final one. Next, we're gonna graph some of the rational functions, and then we also have several inequality problems like polynomial inequalities and rational inequalities. So that's about it.